I just uploaded to the next level of Android. So my phone's still trying to figure it out. I think it's Marshmallow or something. You get an Android phone, you know I'm talking. Lollipop, and now it's Marshmallow. I'm like, whenever I look at my phone, I want to eat some stuff.
108.
108, look at that, sweet. So you just multiply by 3. I like it. So this is a geometric sequence. I keep multiplying by the same thing. So what is A1? 4. What's R? 3. I like it. And what's N? If I want to figure out the sum of these, what would it look like? S, I want S what? Good. 1, 2, 3, 4. I want the sum of the first 4. So N is 4. Yes, ma'am?
Why is R 3?
Because it is. What do I keep multiplying by?
3.
3. There you go. That's why it's called R, because it's the common ratio. Just like D is how much I keep adding for an arithmetic, R is what I keep multiplying by for a geometric.
Oh.
This is 4 times 3. And this is 4 times 3 squared. So forth. Cool. I like it. Yes, sir?
What about the S4? How do you got that?
What about it? If I want to figure out the sum of the first 4 terms, that's what this means. So what does this symbol mean?
Some of the first 100.
Sum of the first 112 terms. I mean, let that be straightforward, right? So if I said this, what does this mean instead?
What is the first one?
What is the 112th term? I like it. So that's just what's the 112th term, whereas this dude says, add up all the first 112 terms. Holy shit, dude, all right. So it shouldn't be surprising that the formula for this is disgusting because it has to do a lot more, don't it? This guy just got to find the 112 term. This guy's got to add them all up. Holy shit. So that it's going to look ugly. Poor little dude. He didn't have a chance. Maybe. So, using all this, let's put this together. So, Sn is that. So, S4 equals, what's A1 again? I'm just going to plug and chug now. What's A1? 4. 1 minus, what's R? 3. What's N? 4. 1, 2, 3, 4 things. Over 1 minus R again? 3. I like it. So do that in the calculator. If you have one.
Couldn't you make that an additive sequence? Because it's always plus 8 times 3 to the n minus 1. It works.
Alright, give it to me.
Alright, so it's 8 plus 8 times 3, and it starts with 0, and then it goes 1, 2.
No. What's your function?
So let me think.
Alright. I shouldn't do it to you because you can't do it, but I just want to see what you come up with. Yes?
So why is that S4 again?
So the sequence exists, right? The sequence keeps going forever. The question would say, find the sum of the first 4. Right? And I just went directly, I just said, here's the first 4. Let's just use a formula to find the 4. And then we can just add them up and see if they're the same. If they're not the same, we did something wrong. So what do you guys get here? This will be 4 times 1 minus 81 over negative 2. So I get negative 2 times negative 80. So I get 160. Is that cool? And what do you get when you add these up? I get 40, 120, 160. When I add them up. So one reason why I call this fall through the cracks math is you could have done this in Math 90. Right? The computations involved here are Math 90 level. You didn't do this in Math 90 because we had too much other shit to do. Right? I think you'll agree with me if you went through Math 90. There's a lot of stuff in there. So that's why I love 120. It's like fall through the cracks. Oh yeah, we could have shown you this. Oh yeah, we could have shown you this. So don't make too much out of this. The computation level of these problems is not really high. I'm going to let you have the formulas on the formula sheet. You just have to understand how to identify the parts that the formula needs for any given sequence I give you. So here, you guys try this one. So I want you to find S11 for this sequence. Now, I did not make it negative yet. It's freaky. don't have a calculator, at least try to set up the equation. If you do have a calculator, try to get the number.
So A1 is the first term?
Yes, always. A1 is the first term, always. What's R here? 5. I like it. See, that's a 5. It's got a flat top. That's a 5. So it'll be 1 minus what? 5 to the?
4.
No. Which one do I want? The sum of the first 11. So n is 11. Yes, sir.
Why is it 11? Because you said.
Because I want the sum of the first 11. That's the question, right?
The
So
question is asking that.
yes, exactly. So I wrote this down, but they're going to say, maybe they'll say find the sum of the first 11. So you know that's S11.
Okay.
So really math cuts through all the bullshit. What is the sum of the first 11 terms? There's a lot of words I don't need there. S11, there you go. All right. And I'm not saying I don't appreciate words. I do. But it's nice to cut through all the bullshit. So S11 is the sum of the first 11. So I want this to the 11th power, because that's what n is. Divided by? 1 minus 5. Cool. You should expect this to be kind of big, right? I mean, this is growing pretty quickly. It is growing exponentially. Who's got a number? See if it matches mine. Anybody have a number they want to throw out there? Like, no, man, it's my number. Try to cheat off of me. All right.
9, 7, 6, 5, 64, 8.
What's the function for the ever-ending? Yeah.
That's exponential, yeah. The one that you just drew?
What's the function for that?
Yeah, well, it's like 2 to the x, 3 to the x, e to the x, could be, right?
Yeah.
E to the x, 2 to the x, 8 to the x. This is like 5 to the x. They all have the same shape. Yeah, but e is the one that you use for population growth
Where
and exponential decay would be.
it never goes.
Yeah, yeah. Throw 2 rabbits in a room and some food. See how quickly the population grows. Or don't. Anybody got that yet? I got this. I got 2, 4, 4, 1, 4062. 2, 4, 4, 1, 4062. Yeah. Anybody get that? See, you should have said it. So when you plug this in, you got to be real careful. If you plug it in all at once, you have to tell your calculator you can't see this bar. You got to put this in parentheses and this in parentheses. So 2 times this in parentheses divided by this in parentheses, or just divided by -4, even better. So make sure right now that you can get this number on your own. Otherwise, your homework is going to be not good. So it's all about plugging in correctly, right? Garbage in, garbage out. That's the old saying. Okay. So that's section 5.7. I want to talk just a little bit about Fibonacci. Any other questions on this here? I mean, I know we suffered a bit through the derivation for this. Hopefully some of you guys saw how it was kind of neat. But even if you didn't, you now have one more formula you can use. You just have to identify each of the parts to it. Okay, cool. So a little bit about Fibonacci. I think we talked about the sequence itself before, right? Well, how the sequence goes. Maybe remember the Fibonacci sequence? I'll start us off. I'm pretty sure we talked a little bit about this before, but maybe not.
2.
Yeah. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8. And so that's a really weirdly defined sequence. It's what's called a recursive sequence. And recursive just means it's built on itself. Right, so there's no external, I'm not just always adding 3 or something external. I'm always adding the 2 previous to get the next one. That's recursive. It's built on itself. Okay, maybe. Does everybody see how to do that? So if I start with the numbers 3 and 7, and I tell you it's Fibonacci-like, what do you think the next term will be? 10, 17, 27, blah, blah, blah. Right? Just keep adding the 2 to get the next one. Now what's really cool, and let me see if I have enough time to do this today, because this is related to the most recent, and you guys don't want to hear this, but the most recent kind of research I've done. So you're like, oh God, he's going to bore us with shit, but I'm going to try not to do that. But it really is kind of nifty cool. There are so many uses to this that while I got Google up here, let me show you just a couple of things. So before we really get into it, if you type in Fibonacci, let's just see what it thinks. If I spelled it right, hey, look at that. Just Fibonacci, you get all this kind of stuff. Fibonacci Finance. So this is what a friend of mine did. He works for, right now he's working for American Express, and he makes a stupid amount of money, but he also has 5 kids, so he spends a stupid amount of money. And he used this in the stock market, the Fibonacci method for the stock market, and he made money over the recession because he used this process. So I think somebody came up and talked to me about this the other day. They actually discovered this in their economics class. And then they were like, is that Fibonacci thing what I learned about in my economics class? And I'm like, yeah, economics stole it from math. So yes, it's the same thing. It's Fibonacci. That's one use for Fibonacci. Yes, ma'am?
Sometimes they use Fibonacci in, like, stocks and stuff like that.
Well, thankfully I don't teach economics. I would so desperately be bored to death in there. But you could go through this and read through it. It's basically counting the number of highs and lows there are, and it refers to if there are 5 highs and lows between 2 things, then you would buy and so forth. I don't know much about the stock market, but in case you're interested, there's at least one student who's learned about this before. I, again, do not teach economics. My point with this is if you go home and you type in Fibonacci something or other, somebody throw out an interest to me.
Hip-hop.
Hip-hop. So Fibonacci, you never know. The parents of hip-hop, no way. Relationship between harmonic notes and music. Fibonacci in popular culture. Hip-hop duo Black Star song Astronomy. Dude.
Oh, that's an amazing song.
There you go. Where'd it go?
Right there, under music.
You see it? There, music, no way. That would give it away. Features the Fibonacci sequence in the chorus. Oh, I see. They just sing about it. There are songs and there are musical characteristics that relate to the Fibonacci. Some songs are kind of silly. This is just the lyrics. They're using in the lyrics reference the Fibonacci sequence. But there are some musical, like this one about the harmonic notes in music. And here's another thing about music. Do any of you guys use an alarm clock to wake up? All right. What's it sound like? Do you guys use? Yeah. There you go. If you don't use the music, it sounds like that. And then think about a very pleasing song, a very pleasing note, or a very pleasing melody. The notes used in conjunction to make that sound are way off from the Fibonacci sequence. If I put 2 notes together that are frequency, that are members of the Fibonacci sequence, it'll sound pleasing to our ear. It's crazy, right? So let me get through. Well, let's see. There's too much to get into here. They've done studies. We'll get into this next time. I think there's just too much. Where if you take a rectangle and you cut it according to the Fibonacci sequence, and we'll get into that next time, how to find that, it's more aesthetically pleasing to our eye. So, for example, what's those little note cards you use? How big are they for notes? 3 by 5? 3 by 5, right? 3 by 5? Or they're 5 by 8? right? Widescreen TV is very often 16 to 9, and we'll see how that's not numbers in here, but the idea with this, one last thing to show you, somebody help me out. If you keep going, you'll get up to here eventually, and then what's the next one, Jeff? You can do it. What's 144 divided by 89? Somebody help me out. 1.6. 1.7, something. And then if I go to the next one, it'd be 233. I think I'm doing that right. 90, 230. Yeah. What's 233 divided by 144? Everybody cool with where I got that from? Just add those together, right?
1.618455556.
So that is called the golden ratio. That, the Egyptian pyramids. We're not sure if they knew about this and they built things according to that measurement, but also it's pleasing to the eye. Things that have this measurement in it are pleasing to the eye. 8 divided by 5 is 1.6, roughly that. 16 divided by 9, what's 16 divided by 9? Help me out there. I think it's like 1.7, I think.
Yeah, 1.7.
Yeah. Pretty close to that, right? So very often things that we need to be aesthetically pleasing will have this number in it. Not because the person that made it knew math, but just because this is biologically pleasing to us somehow, for some reason. And it's because of the fact that the Fibonacci sequence builds on itself, just like organisms and biological things build on themselves. So if you see a tree, last thing, I mean, I can get going on this thing, it's crazy. If you see a tree and you count the number of limbs across, well, I can't even draw a tree. It's great. If you look across at any level, if it's a tree that hasn't been cut and it's been growing nice, it's not been sick, there'll be like one branching, there'll be a trunk, and then there'll be one limb, and then there'll be 2 limbs, and then there'll be 3 limbs, and then there'll be 5 limbs, and then there'll be 8 limbs if you went far enough. Pine cones have this in them. And it's not like magic, it's just in nature. This sequence mimics how nature builds on itself, because the sequence builds on itself. So on one level, it's not surprising that we find it. On another level, it's like, what the freak? What governs me, my view of aesthetics, is somehow involved with this just math freaking playing around with numbers? Yes, that's the short answer.
Oh shit.
Oh shit, that's plenty. So we'll get more into Fibonacci and then the next section next time. Anybody need that project instructions that didn't get that yet? If you don't know what I'm talking about, you probably need it. Sorry. There are due dates on here.
Thank you.
Sure. If you have questions, just come see me.
Our test. Did we get our test?